In 2019, a small submarine began descending into the Pacific Ocean, below the waves, below the shipping lanes, below the world we know. Hour after hour, it kept going down, past the depth where sunlight disappears, past the depth where whales can hunt, past the depth where most life can survive, until eventually it reached the deepest place on Earth. Challenger Deep, nearly 11 kilometers below the surface, a place so remote that fewer people have visited it than have walked on the moon. The scientists inside weren't looking for treasure. They weren't chasing a record. They wanted to see one of the last truly unexplored places on our planet. Maybe they'd find a species nobody had ever seen before. Maybe something completely unexpected. And they did, just not the way they imagined. Lying on the seafloor was a plastic bag, at the deepest known point on Earth. Let that sink in. Our garbage reached one of the most remote places on the planet before we truly explored it ourselves. And that's where this story begins. The more we explored the ocean, the less it made sense. We can land robots on Mars. We can study galaxies billions of light years away. We can detect planets orbiting distant stars. But large parts of our own world remain almost completely unknown. Not because nobody tried, because the ocean doesn't want to be explored. It crushes machines, blocks communication, hides everything from view, and yet life found a way, a world of invisible animals, living lights, creatures that survive without sunlight, entire ecosystems powered by the heat of the Earth itself, and perhaps thousands of species science has never seen. This isn't another planet, it's our planet, and tonight we're going down. At first, this doesn't make much sense. How can a place on our own planet remain so mysterious? It's not hidden behind a distant star. It's not millions of kilometers away. It's right here. So why don't we know more about it? To understand that, we need a little perspective. This is Mars, a frozen desert hundreds of millions of kilometers from Earth. No oceans, no forests, no whales, no life that we've ever found. And yet we've mapped nearly every corner of its surface. We know where ancient rivers once flowed. We know the heights of its mountains, the depths of its canyons. We can land robots there with astonishing precision. Now compare that to our own planet. More than 70% of Earth is covered by ocean. But most people imagine the ocean as a flat blue sheet wrapped around the globe. It isn't. The ocean has depth, and that changes everything. Imagine if life on land existed not only across the ground, but at every altitude from the soil to the edge of space. That's closer to how the ocean actually works. It's not just an area, it's a volume. A vast three-dimensional world filled with life from the surface to the seafloor, which leads to a strange conclusion. If you measured Earth's living space by volume instead of surface area, most of it would belong to the ocean, not to us. And that's what makes this so difficult to ignore. The largest habitat on Earth remains one of the least explored, not because scientists lack curiosity, because reaching it is unbelievably difficult. The first challenge is pressure, the second is isolation, the third is darkness. Together, they create one of the most unforgiving environments on Earth. Pressure is easy to ignore. Right now, you can't feel the atmosphere pressing on your body, but water plays by different rules. Every 10 meters of depth adds another atmosphere of pressure. At 100 meters, the force has already multiplied tenfold. At 1 kilometer, 100 times. And at the bottom of the Mariana Trench, the numbers become almost impossible to imagine. Without protection, the human body wouldn't stand a chance. That's why deep-sea submersibles aren't built like ships. They're built like vaults, small, heavy, reinforced. Every dive is a carefully controlled battle against physics. But pressure isn't the only problem. The moment you descend into the ocean, something else begins to disappear: connection. On the surface, we're surrounded by invisible signals. GPS, cell towers, satellites. The modern world runs on them. Underwater, most of them become useless. Radio waves fade quickly. Satellites can't help you. Even simple communication becomes difficult. It's one of the strange ironies of exploration. An astronaut orbiting Earth can call home. A researcher deep beneath the ocean often can't. And then there's darkness. Most people think of the ocean as bright and blue. That's because almost everything we've ever seen exists near the surface. But sunlight doesn't travel very far underwater. By around 200 meters, the world begins to change. Colors fade, shadows deepen, visibility collapses. Then the light disappears altogether. No sunrise, no sunset, no moonlight, only black water stretching in every direction. For generations, people assumed that life would struggle here. The ocean had other plans. Beyond the reach of sunlight, nature didn't become simpler. It became more inventive. Life near the surface faces a problem that doesn't exist in most environments. There's nowhere to hide, no caves, no forests, no shelter, just open water stretching in every direction. In a place like that, every mistake matters. A predator can spot you from a distance, and you can spot it. For millions of years, animals were pushed toward the same challenge: become faster, become more aware, or disappear. Some species became extraordinary swimmers, others developed remarkable senses. A few took a different path. They became intelligent. Take the bottlenose dolphin. Most people think they know dolphins: friendly, playful, always smiling. But that smile is an illusion. It's simply the shape of their face. The reality is much stranger. Dolphins experience the ocean through sound. They fill the water with rapid clicks. Those sounds travel outward, strike objects, and return. The result is a constantly updated map of their surroundings. Not a visual map, an acoustic one. A dolphin can estimate distance, shape, movement, sometimes even the internal structure of an object. In murky water where a human sees nothing, a dolphin can still hunt with astonishing precision. But information alone isn't enough. The real advantage comes from what dolphins do with it. They share it, they cooperate, they learn from one another, and over time, learning created something unusual: culture. In parts of Australia, dolphins use sea sponges as tools while searching the seafloor. Young dolphins learn the technique from their mothers, not through instinct, through observation, through teaching. Once knowledge begins passing from one generation to the next, something changes. Experience starts to matter as much as genetics. And nowhere is that more obvious than with orcas. Despite the name, killer whales aren't whales at all. They're dolphins, the largest dolphins on Earth, and among the most effective predators ever to evolve. Not because they're stronger than everything else, because they learn. Different groups hunt in completely different ways. Some target fish, others hunt seals, some specialize in sharks. In Antarctica, certain pods create waves to wash seals from floating ice. The technique takes coordination, practice, years of learning. Young orcas spend much of their lives studying older members of the pod. Knowledge becomes tradition. Tradition becomes culture. For a long time, humans believed this was unique to us. The ocean proved otherwise. But intelligence comes at a cost. Big brains require energy, and energy is expensive, especially in an environment where nothing survives alone. Even the largest predators depend on vast networks of life beneath them. Every layer of the ocean depends on another, and some of the most important layers remained hidden for decades, until sonar accidentally revealed them. By the middle of the 20th century, researchers believed they had a reasonable understanding of the ocean. Not a complete understanding, but enough to feel confident. Then the ocean proved them wrong. The story began during World War II. Submarines depended on sonar. Send out a sound, wait for the echo, measure the distance. Simple, reliable, until it wasn't. Operators started reporting something unusual. The seafloor was moving. A submarine would detect what appeared to be solid ground hundreds of meters below. Everything looked normal. Then night arrived, and the seafloor began to rise. Sometimes by hundreds of meters. Before sunrise, it would sink again. The reports came from different ships, different oceans, different crews. Yet the pattern remained the same. The ocean floor seemed to move with the sun. No one could explain it. For years, the phenomenon remained a mystery. Researchers eventually named it the deep scattering layer. Most people preferred another name, the phantom bottom, because that's exactly what it looked like. A false seafloor appearing out of nowhere, then vanishing before dawn. The truth turned out to be even more surprising. The sonar wasn't detecting the seabed, it was detecting life, an unimaginable amount of life. Fish, squid, jellyfish, crustaceans, entire communities suspended in the depths. So many animals gathered in one place that sound waves bounced off them like solid ground. And every night they begin moving, upward, toward the surface, together, not thousands, not millions, billions. It's called the Great Vertical Migration. The largest daily movement of biomass on Earth. Every evening, countless animals rise from the depths to feed. Every morning, they retreat again. The migration happens every day, across enormous regions of the planet, and most people have never heard of it. But life in this layer faces a dangerous problem. There is still enough light to be seen. A predator only needs a silhouette, a shadow, a single mistake. Which is why nature began experimenting with one of its most extraordinary ideas. Not stronger armor, not bigger teeth, invisibility. At first glance, invisibility sounds impossible. Every animal has a shape, a body, an outline, something that gives it away. But the twilight zone rewards only one thing: remaining unseen. There is too much light to disappear into the abyss, yet not enough light to escape detection. A predator looking upward needs only a silhouette, a faint shadow against the glow above. That's enough. So nature began removing the silhouette itself. Some animals became transparent, almost completely, not camouflaged, transparent, skin, muscle. Even internal organs became harder to see. Anything that might cast a shadow became smaller, thinner, or nearly invisible. For millions of years, predators evolved better vision. Prey evolved better ways to vanish. Predators improved. Prey disappeared further. One of the most unusual examples is the barrel-eye fish. For decades, researchers struggled to understand it. Every specimen brought to the surface arrived damaged. Pressure changes destroyed delicate tissues before they could be studied properly. The animal looked incomplete, almost broken. Only when deep-sea cameras finally observed living barrelies did the mystery begin to make sense. The top of its head is transparent. Inside that clear dome sit two bright green eyes, and those eyes can rotate. When the fish searches for food, they point upward, scanning the faint glow above, searching for movement, searching for silhouettes. Then, when prey appears, the eyes rotate forward. The fish locks onto its target and strikes. It's one of the most unusual visual systems ever discovered, not because it's elegant, because it works. And transparency wasn't the end of the story. It was only the beginning, because eventually some animals discovered something even more powerful than invisibility. Instead of hiding from light, they learned how to control it. For us, light is ordinary. The sun rises, the world becomes visible, the sun sets, darkness returns. We've lived with that rhythm for our entire history, but deep below the surface, that rhythm no longer exists. There is no sunrise, no sunset, no dawn, no afternoon, only an endless twilight fading into black water. And yet, the farther you descend, the more light you begin to see. Tiny flashes, brief blue pulses, moving points of light drifting through the abyss. At first it looks beautiful, almost peaceful. It isn't. Every flash means something: a warning, a signal, a trap, a lie. In parts of the deep ocean, most visible animals can produce their own light. Not because it's beautiful, because it's useful. Out here, information can mean the difference between life and death, and light became information. Some animals use it to communicate, others use it to identify members of their own species. Many use it to hunt. Imagine walking through a forest at night. You notice a faint glow ahead, small, harmless, maybe even inviting. You move closer. That's exactly what some deep-sea predators are counting on. The anglerfish carries a glowing lure suspended in front of its mouth. Curious prey approach the light, looking for food, looking for safety, looking for answers. Then the jaws open, and it's over. No chase, no pursuit, just patience. A strategy perfectly suited for a world where every calorie matters. Other species use light in a completely different way, not to attract attention, to avoid it. Many deep-sea hunters search for silhouettes against the faint glow filtering down from above. Some squid and fish solve the problem by producing their own light along the underside of their bodies, just enough to match the brightness overhead. From below, their outline disappears. The animal effectively erases itself from view, a living stealth system. Millions of years before humans imagined one. Again and again, nature arrived at the same conclusion. Control the light, and you control information. Control information, and you improve your odds of survival. But eventually, even light stops solving the problem. Because far below these glowing worlds lies a challenge no adaptation can fully escape. A shortage of food. And down there, every calorie becomes precious. Far below the glowing world of bioluminescence, another problem begins to dominate everything: food. or more accurately, the lack of it. Near the surface, energy is everywhere. Sunlight feeds plankton. Plankton feeds fish. Fish feed larger fish. Life constantly creates opportunities for more life. But thousands of meters below, that system begins to fade. Nothing grows here, no forests, no algae, no sunlight. Most of the food arriving in these depths comes from above. Tiny fragments drifting downward through the water, dead plankton, dead fish, microscopic remains of life from the surface. Marine biologists call it marine snow. The name sounds peaceful. The reality is far less romantic. For many deep-sea animals, this endless snowfall is the difference between survival and starvation. Imagine living in a desert where food arrives randomly from the sky, sometimes today, sometimes weeks from now. That's the reality for countless animals below. Every meal is uncertain. Every calorie matters. And when resources become scarce, everything changes. Movement changes, growth changes, behavior changes. The animals that survive aren't necessarily the strongest. They're the most efficient. Few creatures demonstrate that better than the vampire squid. At first glance, it looks like something from a nightmare. Dark body, large eyes, webbed arms. Even its name sounds threatening. But appearances can be deceptive. The vampire squid is not an aggressive hunter. Most of the time, it barely moves. Instead of chasing food, it waits for food to come to it. Using long, sticky filaments, it collects drifting organic particles from the water. Tiny meals, tiny rewards, but enough. In a place where every calorie matters, wasting energy can be fatal. And that's one of the most important lessons of the deep ocean. Success isn't always about getting more. Sometimes it's about needing less. But nature didn't stop there. Some animals became so efficient that life itself began operating at a different pace. Cold temperatures slowed metabolism. Scarce resources slowed growth. Everything moved more slowly. Years became decades. And familiar creatures began changing in unexpected ways. Scientists call one of these patterns deep-sea gigantism. In some groups, animals that remain small near the surface become giants in the depths. Take the giant isopod. Its distant relatives are tiny creatures most people would never notice. The deep-sea version can grow larger than a football, armored, patient, capable of surviving long periods without food. Then there are siphonophores, some of the longest animals ever recorded. Not a single organism, but vast colonies functioning as one. Some stretch for tens of meters through the abyss. Longer than many whales, longer than a city bus. The deeper researchers explored, the clearer the pattern became. The deep ocean isn't a place where life failed. It's a place where life slowed down. Everything here is built around patience. Patience in movement, patience in growth, patience in survival. And nowhere is that idea more extreme than in a predator that may live for centuries. A creature so old that some individuals swimming today were already alive before the modern world existed. If you spend enough time studying the deep ocean, one pattern appears again and again. Everything slows down, movement slows down, growth slows down. Even survival seems to operate on a different schedule. Near the surface, life is a race. Animals compete for food, for territory, for mates. Every day matters. In the deep ocean, that urgency begins to fade. The environment rewards a different strategy. Wait, conserve energy. Outlast everyone else. No creature represents that idea better than the Greenland shark. At first glance, it looks surprisingly ordinary. No glowing organs, no transparent head, no bizarre appearance. Just a large shark moving through cold, dark water. Slowly, very slowly. For years, few people paid much attention to it. Then researchers began asking a simple question. How old are these animals? The answer seemed impossible. Some Greenland sharks are estimated to live for more than 4 centuries. Think about that. When some of these sharks were born, Shakespeare was still writing plays. Entire nations had yet to exist. Generations of people lived and died. The shark kept swimming, not fast, not far, just steadily, year after year, century after century. Its secret isn't strength, it's efficiency. Everything about its biology is designed around conservation. Spend less, need less, live longer. The deep ocean reached that conclusion millions of years ago, but even the most patient predator eventually needs food. And in the deep sea, a large meal is rare, extremely rare. which is why, when one finally arrives, entire ecosystems respond. Imagine a fully stocked supermarket appearing in the middle of a desert. That's essentially what happens when a whale dies. A whale may spend decades crossing the oceans. Then one day it sinks, down through the water column, into the depths. Eventually, it reaches the seafloor, and almost immediately, life begins to gather. The scent spreads for kilometers. Scavengers arrive first: fish, crabs, sharks, anything capable of finding a meal. For months, sometimes years, the carcass feeds an entire community. But even after the flesh disappears, the story isn't over. The skeleton still contains enormous amounts of nutrients, and that's when some of the most unusual organisms in the ocean appear. Bone-eating worms, tiny animals capable of extracting nutrients directly from whale bones. A single skeleton can support life for decades. One dead whale, feeding generations of creatures. For centuries, researchers assumed this was about as independent as a deep-sea ecosystem could become. After all, the whales still depended on the sun. Everything still traced back to sunlight. That assumption survived for generations. Then, in 1977, it collapsed. For centuries, one idea seemed almost impossible to challenge. Life depends on sunlight. Different ecosystems may look different. A rainforest isn't a coral reef isn't a grassland. But beneath those differences, the same rule always seemed to apply. Energy comes from the sun. It was one of the most fundamental assumptions in biology. And then, in 1977, a group of researchers went looking for geology. Instead, they found a revolution. The expedition was exploring the Galapagos Rift in the Pacific Ocean. The mission was straightforward: study the seafloor, map volcanic activity, learn more about how Earth's crust changes over time. Nobody expected a biological discovery, especially not one that would challenge a centuries-old belief. As the submersible descended, black water surrounded the crew. Rock, sediment, more rock. Then something appeared. Towering structures rising from the seafloor, some taller than a house. Dark clouds poured from their tops, like smoke from industrial chimneys. Except there were no factories here, no cities, no sunlight, nothing but the deep. The structures became known as hydrothermal vents, more commonly black smokers. Cracks in Earth's crust where seawater seeps underground, heats up, and returns carrying dissolved minerals from deep within the planet. The environment should have been hostile to life. Temperatures near the vents can exceed 400 degrees Celsius. The water is rich in toxic chemicals. The pressure is immense. By every traditional assumption, this should have been a biological wasteland. Instead, it was crowded with life. Everywhere the crew looked, animals covered the seafloor: giant clams, crabs, shrimp, dense communities thriving where almost nothing should survive. And then they noticed something even more puzzling: massive tube worms, some longer than a person. Bright red at the top, pale white below. They looked almost unreal. Naturally, researchers wanted to know what they were eating. The answer made no sense. The worms had no mouth, no stomach, no digestive system at all, an animal with no obvious way to eat. At least, that's what it seemed. The real explanation was far more astonishing. Inside the worms lived billions of bacteria, and those bacteria had discovered another way to power life. Instead of using sunlight, they used chemistry. Hydrogen sulfide pours from hydrothermal vents. To most animals, it's poisonous. To these bacteria, it's fuel. They convert chemicals into energy, energy into food, and food into an entire ecosystem. No sunlight required. For the first time, researchers had discovered a complex community built on a completely different foundation. Life wasn't feeding on the sun, it was feeding on the Earth itself. That realization changed everything, because the discovery wasn't really about tube worms or clams or hydrothermal vents. It was about possibility. If life could thrive here, in total isolation from sunlight, under crushing pressure, surrounded by toxic chemicals, then where exactly are the limits? Suddenly, places that once seemed impossible started looking different. The frozen ocean beneath Europa, the hidden seas of Enceladus, underground oceans locked beneath ice, worlds once dismissed as lifeless, worlds that suddenly looked a lot more familiar. The search for alien life didn't begin with a telescope. It began with a dive into the depths of our own planet. And perhaps the most surprising part of all, the most alien environment humanity had ever discovered wasn't in space. It was right here on Earth. If hydrothermal vents changed our understanding of life, the Mariana Trench challenged our assumptions about its limits. For decades, researchers believed there had to be a boundary, a depth where pressure became too extreme, a point where biology simply stopped. The logic seemed reasonable. As conditions become more hostile, fewer organisms survive. Push those conditions far enough, and eventually nothing should remain. At least, that's what we expected. The Mariana Trench had other ideas. Stretching more than 2,500 kilometers across the western Pacific, it is the deepest ocean trench on Earth. At its lowest point lies Challenger Deep, nearly 11 kilometers beneath the surface, a place untouched by sunlight, a place where pressure exceeds 1,000 times what we experience at sea level, enough to destroy most machines, enough to crush a conventional submarine, enough to make survival seem impossible. And yet life is here, not abundant, not easy to find, but undeniably present. When the first expeditions reached these depths, many expected little more than microbes. Instead, they found an ecosystem, small crustaceans, sea cucumbers, worms, microbial communities, and eventually something nobody expected: fish, living fish. The deepest fish ever observed, the Mariana snailfish. At first glance, it looks fragile. Its body is soft. Its bones are lightly built. Its skin appears almost delicate, exactly the opposite of what most people imagine surviving under extreme pressure. But that's the lesson. Life rarely solves problems the way we do. Engineers fight pressure with stronger materials. The snailfish avoids the fight altogether. Its body is designed to function within the pressure rather than resist it. Instead of battling its environment, it becomes part of it. Again and again, the ocean delivers the same message. Survival isn't always about strength. Often it's about adaptation. The strongest creature isn't necessarily the one that wins. It's the one that fits. And every time humanity believed it had discovered the limits of life, life quietly moved the boundary. A little deeper, a little further, a little beyond expectation. Which raises an uncomfortable possibility. Maybe the limits we imagine for life say more about us than they do about life itself. Throughout this journey, one pattern has appeared again and again. We thought darkness would be the limit. It wasn't. We thought pressure would be the limit. It wasn't. We thought the absence of sunlight would be the limit. It wasn't. Again and again, the ocean forced us to reconsider what was possible. And after everything we've seen, one question remains. If the largest unexplored world on Earth can still surprise us this much, what else haven't we found yet? At the beginning of this journey, we talked about a plastic bag, a simple piece of trash resting nearly 11 kilometers beneath the ocean's surface. At the time, it felt like a depressing detail, a reminder that human influence now reaches almost every corner of the planet. But after everything we've seen, that plastic bag tells a different story. Not because of what it is, because of where it was found. Think about it. To reach that place required years of planning, specialized vessels, advanced engineering, and some of the most sophisticated technology humanity has ever built. Yet even today, vast regions of the ocean remain unexplored. Not unmapped, unexplored. There's a difference. A map can show you where a mountain is. It can't tell you what lives on it. A map can reveal a trench. It can't tell you what survives inside it. And that's the reality of the ocean. The largest habitat on Earth still exists partly beyond our understanding. Somewhere in those depths, there are almost certainly species we've never seen, behaviors we've never observed, relationships we've never imagined, not because they're hiding, because we haven't looked. For most of human history, mystery lived beyond the horizon, then beyond the atmosphere, then beyond the solar system. We became fascinated by distant worlds, and for good reason. Mars is fascinating. The moons of Jupiter are fascinating. The possibility of life elsewhere in the universe is fascinating, but exploration sometimes creates an illusion, the illusion that all the great discoveries lie somewhere far away. The ocean quietly challenges that idea, because one of the most alien worlds ever discovered isn't orbiting another star. It isn't hidden in a distant galaxy. It's here, on the same planet where we built cities, flew airplanes, split the atom, and walked on the moon. A world of living lights, invisible hunters, creatures older than nations, and ecosystems thriving where life should be impossible. A world that has been beneath us this entire time, waiting to be understood. And maybe that's the most remarkable part of this story. After every map we've drawn, every satellite we've launched, every telescope we've pointed toward the sky, we're still surrounded by mystery, not at the edge of the universe, at the edge of our own understanding. And somewhere tonight, far below the waves, life is doing what it has always done, surviving, adapting, evolving. While we search the universe for answers, one of the greatest mysteries on Earth is still waiting below.